Here we have what is called constraint optimization problem. A producer is producing a good and utilizing two inputs x and y. The cost function of utilizing these inputs is this, 8x squared minus xy plus 2y squared. It is also called the objective function in our context. The inputs can be measured in fractional units. However, the total amount utilized must remain 42 units. Different input ratios result in different costs. The objective is to find the input ratio of 42 units that minimizes cost.
Let's visualize the cost function, which is a three-dimensional surface. Input the function into Mathematica. This is three-dimensional surface of the cost function. X-axis and Y-axis make a plane on the ground, and the cost is measured along the Z-axis, the third dimension. We can rotate the surface to view it from different angles. From the origin here, it lifts upward along both axes until it is of the maximum rise.
Let's locate and read some random points on the surface. This one gives us a combination or ratio of 26.92 units of x and 14.46 units of y, having cost of 5,800, 24.43 units of currency. Constraint line is added as Parametric plot 3D. Note that one end of the line is at 42 on x-axis and the other at 42 on y-axis. Any point on this line gives us a ratio of x and y that adds up to 42. Any point below this line towards origin gives a ratio of x and y with a sum less than 42. Any point above this line gives a ratio of x and y with a sum more than 42. Therefore, for our best ratio, we must remain on this line and find a point where cost is minimized.
Have a look at the Mathematica code for the following important diagram. In this diagram, blue and green points are randomly generated. With each keystroke, these 2 points change. However, green point remains on the constraint line, even after changing its previous location. The dark red point is fixed and represents the optimum, cost-minimized point on the constraint line, as determined by the Lagrangian method. By rotating the diagram to view it from different angles, we can see that the dark red point indeed corresponds to the minimum possible cost for the given input ratio of 42. The optimum x value is 9.55. The optimum y value is 32.45, with corresponding minimum possible cost of 2,525.73 units of the currency. The cost associated with the green point on either side of the dark red optimum point exceeds the minimum cost. Now, let's turn to the Lagrangian method to find the optimal point. To define Lagrangian function L, first we rearrange the constraint and set it equal to 0. X plus y is equal to 42. Rearrange. 42 minus x minus y equal to 0. Multiply it with Lagrangian multiplier lambda. Adding this product to the objective function gives us the Lagrangian function.
Take derivatives and set them equal to 0. First, take derivative with respect to x. 8x squared is 16x. Minus xy is minus y. And minus lambda x is minus lambda. Next, take derivative with respect to y. Minus xy is minus x. 2y squared is 4y. And minus lambda y is minus lambda. Take derivative with respect to lambda. Which is the constraint in rearranged form. We have now 3 unknowns in 3 equations. Subtracting these 2 equations cancels out lambda, and we have 17x minus 5y equal to 0. We have eliminated lambda, and now this equation is in 2 variables, x and y. So, now we have 2 equations in 2 unknowns, x and y. Solve constraint equation for y. Put the value of y in previous equation and solve for x. Put the x value in the constraint to find value of y. Put the values of x and y in objective or cost function to find the optimum or the minimum cost. Confirm the results with Mathematica solve function.